as, file saved as, computer document, see how to program. Okay, this is the entire textbook that I'm posting up there now, so. Oh, nope. I'm not posting it there because it's too large. So. So I'm going to go ahead and post just the first chapter right there. So I'm going to do it chapter by chapter. Right there. And let me go ahead and post week 2 as well. Maybe. The posting is taking a while. I gotta wait till I post before I can add anybody to the group. So, actually, anybody who's already a member of the group can add the person. I don't know what's taking so long. All right, I'm gonna go ahead and get started right there. Right there. Okay, it's already recording. Oh, okay. All right. Okay. There. I don't know how much I did on these slides, probably not very much, so I'm just going to go ahead and start from the beginning again, right there. So, there. So as I recall, actually I'm using a different resolution. Let's see. Hey, it actually works with this, with the HDMI setting right there. So I can actually write on the screens now. Right there. So I don't know what's going on with this projector. Right there. Okay, right there. So the first chapter is just basically right there. I'd like to, at the end of the day, have you write a short little program right there. So right there. So we'll go through right there to give you your first shot at writing something. Right there. Last time we did not do that. Right there. So okay, I talked a little bit about some of this, but as I said, I'm going to start over again. Right there. I'm not going to go through the outline again. It's that there. It's a long outline. I could spend an hour just talking about the outline. Right there. Right there. The book that we're going to be using right there is the Decto book. I've used Decto books probably for 10 years, 15 years. It's written by a father and son group. The father wrote the first group of books. He's gotten old and out of date, probably like myself, and his son picked him up right there. So his son is probably wrote this particular version right there. So, right there. So I will probably put the example programs up later. I've downloaded them all. I just haven't posted them right there. So, right there. Software is a set of instructions. I talked last time about, you know, I compared it to how you would change the engine on a motorcycle. You would go through the instruction manual step by step, that there, and I also referred to it as making nasi lemak. You would follow it step by step, right there. Software is the instructions we're asking the computer to do out there. And we will go through some examples of that, many examples of that there. The one thing computers do quicker than humans is that they can do calculations much quicker. If I want to calculate someone's pay, for example, right there, I have several inputs. One is the number of hours they work, and we're going to assume that we're paying this worker by hour. It's their pay rate per hour. Their pay rate per hour, right there. We would have their income tax rate. We'll assume that they have to pay income tax. We have to withhold that. We would also have to know whether or not we withhold any, what do they call that? Your employee's provident fund, EPF rate, right there. Is there anything else that we need to know? We'll just assume that that's 4 is enough, right there. So your gross pay is equal to your pay rate times hours worked right there. Your EPF, what's going on here? It was working earlier. EPF is equal to EPF rate times your gross pay, right there. Your income tax is equal to tax rate times gross pay. I think that's everything right there, yeah. So your net pay is equal to your gross pay minus EPF minus income tax. Right there. And we will call transfer, and we will then take your employee number and all that, and we would transfer it to your bank account, and we go through the rest of that. But this is a basic idea of how you would calculate somebody's pay, right? Right there. Well, if I have a huge file where I can read each employee and I read their employee number, then I can look up in the file what their pay rate is, their gross pay, right there. So my file would include the employee number and the number of hours they worked. I could calculate their next pay. I can look up what bank they have, transfer the money into their bank account, and do pay rate, the payroll in about 12 seconds versus going through and calculating each person's pay one by one and then logging into the bank and doing the transfer manually. So writing a program to do someone's pay makes sense, right? They could do this very quickly. So going back to our instructions here, computers can perform calculations and make logical decisions potentially faster than humans, right there. In other words, I can do the payroll for all of UniKL BMI very fast if I know everybody's pay rate right there. Now, most people here are paid by the month, so it's actually easier because it doesn't change from month to month, but we'll assume that we have hourly employees like you would have in a factory or a food shop or something like that there. So today's personal computers can perform billions of instructions in 1 second right there. So when we look at a typical i7 processor, it has a clock speed of about 3 point something, we'll say 3.5 gigahertz. A gigahertz is 1 billion clock cycles per, so 3.5 billion clock cycles per second. And let's say it takes 3 clock cycles to execute one instruction, so it's roughly 1 billion instructions per second, roughly, out there. So it's very, very fast, right there. You know, I suspect that most of you will pick on the guys here. If you play football, right, you can't make a decision on whether or not where to kick that ball in 1 billionth of a second, right there. You don't even know where the ball is at 1 billionth of a second, because who is it? I can't even, Heisenberg's uncertainty principle says that you can't know where an object is at any particular exact moment in time, and 1 billionth of a second is an exact moment in time, right there. So according to Heisenberg's uncertainty principle, you don't know where that football is, let alone how to kick it in 1 billionth of a second, right there. There are supercomputers that are 1,000 times faster, 1 million times faster than desktop computers, right there. We write computer programs. I gave you a short example of a computer program, right there. So that their programs guide the computer through ordered actions, right there. And the people who write computer programmers are called programmers, right there. So, and by the way, programmers are probably not the highest paid computer professional out there. You know, a lot of people will start off as programmers, but then they end up migrating to other, other occupations, right there. So we have 2 things when we talk about computers. Actually, there's a third one. I'm going to write down here, firmware, right there. And software is the computer program, something you write. It actually resides on the hard drive, or that's there, or used to be it would reside on a floppy or a CD or a thumb drive, but it's the code in which is executed. The hardware is the physical stuff that you can touch, right there. Now firmware, it kind of goes in between the two of those. It's actually software that's programmed into the chips on the computer itself, right there. So when we look at embedded systems, right there, a lot of what we look at is firmware. So if we look at, for example, a microwave oven, everyone's used a microwave oven, right? Yeah, that there. So a microwave oven has a keypad, it has a LED display or LCD display, it has a push button to open the door, it has a Megatron that provides the heat right there, it has a spindle that turns the food around in many cases, most cases today, right there. That is driven by a computer chip, right there. A microcontroller or a microprocessor drives that microwave oven. It's every bit a computer as this desktop computer that I'm using here, or your laptop is, or that computer that's there. It's just that it's a dedicated embedded system right there. The software for that microwave oven is programmed into a chip on the microwave oven right there. It's still software, but you can't change it right there. Now some modern ones actually have flash memory, and you can take a USB drive and open the back and plug it into a particular USB port and change it that way, but the user cannot normally update the firmware inside their microwave oven right there. So it's firm in the fact that it can't be changed by the user, but it's soft in the fact that the manufacturer could change it at any time when they design that there. So the hardware, of course, is the actual physical microwave oven, the microprocessor, the memory, all that there. But the code that drives the microwave oven is often referred to as firmware. And firmware is where I've spent probably 75% of my career right there, is writing firmware right there. And firmware is a type of software right there. So, I think I mentioned this before, computers used to fill a large room right there. When I first started working as a student, we'll go back to when I was a student. The university I went to used an IBM 370 whatever computer system right there, and it was about size of half this room right there. We would write our computer programs on a card punch reader or card punch machine. We would type in, and every time we hit the enter key, it would spit out a new card, and each line of code was one card right there. And to run our program, we would take our stack of cards, put it in the card reader. The card reader was probably about the size of this table, only this big right there. It was pretty large right there. And it would read the cards that they're really fast right there. And then 20, 30 minutes later, a printout would show up in my little box right there, like the faculty mailboxes downstairs where where you would submit work, these little mail pigeonholes that there. We call them pigeonholes. I don't know what you would call them here, but they're little boxes about, maybe, I want to say maybe 20 centimeters by 20 centimeters, large enough to put a piece of mail in. They would roll the printout and stick it in that box with my student number right there. And then I would look at my code, figure out where my mistakes were, go back to the card punch machine, find the cards with the errors in them, and retype them right there. So if you dropped a stack of cards, it was like shuffling. If you imagine a deck of 52 playing cards, and you have them ordered ace, spades, ace through king, and then hearts, ace through king, and you drop that deck of cards, and you had to put them back in order. That's the way it was with that. The only difference was they weren't as easy because each card had a line of code, and so you had to try to figure out what the order was. So you didn't drop your cards very often, right there. So, but computers have changed a lot. I'm going back 35 years before your parents were even born, right? Well, your parents were born, but before they were in high school, right? That's there. Most of you are in your 20s. We'll assume that your parents were in their mid-20s. So if I go back 35 years ago, your parents would have been 15, 16 years old right there. So I'm old enough now that I've got the second generation of students that they were back at my old university. I had their parents as students. Now I'm having them as students. That was having them as students. So many decades, these costs have fallen. Again, this has been an additive effect. My first desktop computer that I bought, and I say a real computer, was an IBM PC 5150. Nobody's going to know that number unless you're a real computer geek and you follow history. That was the original IBM PC, right there. Right there. And that particular computer came with an 8088 processor, which was an 8-bit / 16-bit processor. It came, if you bought it off the shelf, with 16K of RAM. I bought it with 64K of RAM. I paid extra and got more memory. I bought it with two floppies. It came with one floppy right there. I bought the deluxe model that there. Hard drives weren't out yet. You couldn't buy a personal hard drive yet, so there was no hard drive right there. I bought a dot matrix printer. Laser printers weren't out. Jet ink printers. It was a black and white printer right there. I bought a monitor that I could push a button, and it could be either green, amber, or white. There was no color monitors that I could afford. And that system back in 1984 was when I bought this, 83, 84, cost $3,000 US roughly, right there. So, that's there. I'm talking big money to buy a system today. $3,000 will buy you an awfully nice system. Now, I'm also talking $1983 here, which would be the equivalent of about $15,000 USD, or 50,000 RM, you know, for that system. If you can imagine what you would get for 50,000 RM today as far as computer systems go, right there. You know, so it's right there. This trend was defined by a guy by the name of Moore, Gordon Moore. He was one of the co-founders of Intel back in the 60s, right there. Intel was one of the early semiconductor companies. Matter of fact, Intel invented the microprocessor. The microprocessor was actually a chip designed to do programmable operations. They actually designed the chip for a customer. The original customer was a Japanese calculator manufacturer, Casio, or one of the Japanese companies that made calculators right there. After they designed the chip, they thought it was a really neat chip, and they maintained the rights to the chip, or bought the rights from the chip. I can't remember the details. I think they bought the rights from the chip right there. And because they thought it could be used for other things. This was in the early 1960s, and this chip was called a 4004 right there. They decided 4 bits wasn't enough right there. We'll talk about bit size, possibly not in this class. You'll probably look at it in your digital courses or your microprocessor course. You know, they doubled the size of the chip to an 8-bit chip, called it an 8008. They made some changes and then called it an 8080. And that was the first released microprocessor, was the 8080. And that came out about 65, 66, something like that there. I can't remember. And then after the 8080 was the 8085, then the 8086, 8088, the 188, 186, 286, the Pentium. They all grew out of this family. So Intel is the granddaddy of microprocessors. They're still in business. They still make chips. They still make the i5, i3, i7 series that are used in most desktop computers today. They also make a smaller series, you know, the M series for their small tablets right there. That's there, and they're not really big in the cell phone market. You don't find them. They don't make cell phone chips right there. Most of those are ARM processors made by Samsung, Apple. Atmel makes some of the ARM processors. So cell phones typically aren't using Intel chips right there. At one time, there was a company that competed with Intel called Motorola. Motorola sold off that division of Motorola. It became Freescale, which is still in business today, but they don't sell a lot of chips. You know, that there. They sell some, but they kind of left the computer chip business as much. They used to sell the 68000 series, which competed with the Intel chips, and almost all the Apple Macintoshes used the 68000. Hewlett-Packard used them, and they were in most of the Unix machines. So AT&T and Bell Labs used them, and Motorola switched over to the Intel, or not Motorola, Apple switched over to the Intel probably 10 years ago, and that pretty much killed the 68000 business back there. Motorola originally was a radio manufacturer. They made radios for police departments and fire departments and that there, a lot of military type radios. So they kind of accidentally got into the computer industry with cell phones. It's not their mainstay, and they sold it off. And that there's still the Freescale 6800 series is still around for embedded systems, but that's there. But again, Intel is the granddaddy right there. Intel has been around for a long. The Moore's Law is still around. Moore's Law. If you look at flash memory, for example, 3-4 years ago, the largest flash memory you're going to find was 16 gig, right? Now you can buy 128 and 256 gig memory chips. You know, that's there. I think I've got a 200 gig in my this laptop right here, as far as a micro SD card for my extended memory, right there. So it's still growing. Similar growth is applied in the communications field. You got to remember that hand phones today are computers, right? Right there. If we look at a modern hand phone, it is a computer that happens to make phone calls. Right there. So it would make sense that the communications field has doubled. In a prior lifetime, back in the 1970s, I was in the Air Force, in the communications field to a large, that there, kind of a sideline, and people were still using Morse code to communicate. That there, military electronics or military communications, especially the Soviet bloc and a lot of the developing world. Morse code was the primary form of communications. If anybody's ever heard Morse code, it's very slow and very hard to decipher. You have to know Morse code to understand it. That there, I probably still to this day would be able to, write down a Morse code message if I hear it, because I did it for so long, so regularly, right? That there. But Morse code, we were talking extremely fast at 40 to 50 words per minute, right there. When we talk about shipping off an email to somebody, it's transmitted something like 2 or 3 million words per minute, right there. So, right there. The other difference was Morse code, if you wanted to encrypt it, you had to encrypt it before you sent it, right there. So, and then even once the receiver received the message, he could try to decipher the message right there. So codes were a big thing with Morse code right there. Actually, that's what I did. That was my major job, was working in the code area right there. But right there. But regardless, Morse code was set in groups of 5 encoded messages, and we would get those coded messages and try to decipher what the original content was out there. Nowadays, emails are broken into packets, sent over the internet. They can be scrambled in such a way that it's very, very difficult to decipher those. I mean, and there are 3-letter agencies in both the U.S. and the Soviet Union, or the old Soviet Union, Russia, and the U.K. that try to decipher that there. MI6 is still, which is military intelligence number 6. MI6 is still trying to do it. National Security Agency in the U.S. still tries to do it. I don't know what the equivalent of the KGB in Russia is, but there is a 3-letter organization in the old Russia that tries to do the spy work in terms of communications deciphering. But as far as the U.S. goes, it's MI6 and NSA are the 2 groups that do that type of work. But again, their whole goal is to try to decipher messages out there. So costs have plummeted right there. So things have gotten cheaper right there. So, okay, now we get into our actual material. We have an input unit, an output unit, memory unit, ALU, and CPU. And I think I gave a different grouping last time, right? I think last time, right there, and I said we have inputs, we have our CPU, which incorporates the ALU. They're both there. We have our outputs, and then we have storage right there. Right there. I think that's the model I gave last time, right there. And the exact model is not going to be on the final exam, so you don't have to worry. Actually, this class doesn't have a final exam, so it doesn't matter about studying and remembering the exact model. But this is where we write our computer programs. They go into the CPU. And our CPU is going to take our inputs, possibly stuff from our secondary storage, right there. In other words, going back to my payroll example, I may look up my input may be an employee number and hours work are our only two, and I have to go to the secondary storage, look up that employee's file, and find out what his pay rate is, what his EPF rate is, what his tax rate is. All that stuff is coming out of the secondary storage. Now, I don't know how taxes are figured in Malaysia. I have no clue on Malaysian tax law. U.S. uses a sliding scale depending on the number of dependents that's there. So the tax rate may have to be calculated. Malaysia, I think it's a fixed rate right there. But regardless, I did my taxes last year. I don't know. I just filled out the form, and then they told me how much money I owed them or they owed me back, and that there. But regardless, that there. But secondary storage may contain inputs. We may write back to our secondary storage how much money this person gets paid this month, for example. That way, at the end of the year, we can print out another document saying what the annual pay was for the employee. So secondary storage works both ways. It can be an input or an output depending on our code. And our outputs, of course, are printers, the screen, that their banking information. The internet can be a message to CIMB saying, into such and such an account, please deposit 680 ringgits from this account. In other words, transfer from our payroll account into the employee's personal account how much money they're paid this month, right there. So that may be an output, may be a message to CIMB saying to pay somebody right there. So, but this is the basic model that we're looking at in terms of right there. So I talked last time about data hierarchy. Again, I'm repeating a little bit of what I talked about last week. One, it's been a week since I've covered it. That's there. And two, it doesn't hurt to cover it a second time. Right there. We can get very complex with data structures. We're going to keep them simple right there. But when we look at data structures right there, and for example, let's look at a data structure for an employee right there. And employee type right there. Let's just call it an employee type right there. But we'll talk about what defines a type and what defines that there. An employee is going to have various parts to this data structure right there. So the first thing it's going to have is a given name, their father's name. Now this is different if you're dealing with a Western, because my father's name was George, but there's no George in my name right there. My original name used the family name, right? Your last name right there. Islamic names are Muhammad bin Shafi'i, right? Right here. Well, I'm Shafi'i, but I'm trying to make up a name off the top. Azim, right? So your father's name is Azim. So your name is Muhammad bin Azim, right? So, but that, again, that's your name. You may have a date of birth right there. That may be part of your name, part of your field right there. You may have whether or not you're married. You may have your wife's name. Given and father's again, right there. You may have your pay rate. Right there, we talked about pay rate. That's stored in your employee file. We may have your tax rate. Your tax rate's different than if you're an expat. We may have your IC number right there. We may have place of birth. We may have job title right there. We may have department number. What department are you in? Who is your supervisor? Right there. Children. Number. The number of children. Names of children. right there. Date of birth of children. I mean, you can see we could have all kinds of information on a particular employee stored in their employee record. Now, we may not have all of this. I'm just making things up that we would put into that there. And this would be stored in a database somewhere, my employee database. I want to print paychecks. I go to the database, and based on, say, the IC number, I find that employee right there. Once I find that employee, I get their pay rate, I get their tax rate. The number of hours they worked is already in the employee or the weekly payroll file, right? So I can now calculate their pay. You know, one of the things we may have is bank name and account, bank account number, right there. So we get the bank, what bank are they with and what their account number is, and we can calculate their pay and make the transfer. So what we're looking at is in this employee file is the rest of the information I need, right there. So going back to our data hierarchy is data items are processed from computer's former data hierarchy, which becomes larger, more complex as we progress to more and more data, complex data types. I just gave you a very complex one with that employee file. There has lots and lots of information right there. And trust me, UniKL has a file on you in their computer system right there, because I can look at it. You know, as your instructor, I can pull up a particular student. I can look at your, your employee, your student, your IC number, see how many courses you've taken, what your grades have been, where you're from. That information is available right there. In some cases, a photograph is included right there. If you look at, for example, JPJ database, you get a license to drive a car. Your photograph is then stored as part of the database, right? Out there, it's scanned in or taken right there. So here again, we're looking at data hierarchy. We've got Sally Black is her name, first name and last name, right there. We have some blank fields that have not been filled in, right there. We've got there. Now Judy itself is an array of strings or of characters. Each character is a number. This is the number. The letter J is represented by these 8 bits right there, and a bit is a 1 or 0 right there. Now we won't get down to this level in this class. In digital and microprocessors, you will get down to that level. We will stay more up in this level right here. Right there. So we've got bits is the smallest one, it's a 1 or 0. A character is a letter, right there. A field can be a string or it could be a number, right there. A record is a bunch of fields put in there. What I gave you for employee was an employee record. The field would be something such as their given name. That would be a field right there. And that particular field is a particular group of characters right there. So, when we set up our programs, we have to keep in mind that we're going to be talking about data, and data can be simple or it can be complex. This class, we're going to keep it relatively simple, obviously. It's a freshman level course right there. But it can get quite out there. A file is a group of records right there. We've already mentioned the fact that we would have a file of all the employees that would be kept in a file. A database is a collection of data. It can be multiple files that are related to each other somehow right there. So for example, there may be a file of employees that work for different supervisors. So we have a file of supervisors for each supervisor, we would have the department they're in, what that particular department does, and we would have a list of employees that work for that particular supervisor. Well, we wouldn't have all the employee information in the supervisor's file. That would refer back to the employee file. So I look up at Scott Nahak, I'm a supervisor, and Siti Norazam works for me right there. I would just have Siti Norazam and her IC number. If I want to know about Siti, I would then go to the employee file and get the information from there. So, that there. So if I wanted to calculate the average salary of all the employees that work for me, I wouldn't look up the salary in my file. I would go through and look up the employees in my file, go to their employee records and pull up their salary right there. So these are tied to each other through a database right there. There are programs out there called database managers that you would then use to design databases and tie them together. You typically would not write a database using C or C++. You would use a database manager tool to design your database, and you might write certain functions in the database using different software packages that there. The number one database software used is actually Visual Basic right there. Accesses the database manager package given to us with Microsoft Office. It includes a program called Access used to design databases. We're not going to design any databases. I may do a demo later in this semester on that there. But a database manager allows us to design databases and connect to them and graphically see how they interconnect each other. And then big data is, of course, I mentioned this last time, is as much data as we can get on everybody right there. Companies that specialize in big data try to find out everything they can find about you right there. And, an example of that is, anybody ever use a program called Foursquare? Out there, it's a little restaurant package out there. Out there, and a lot of these programs actually have GPSs, and it's pretty scary. You carry your phone with you everywhere, right? And your phone's got the GPS turned on, right? Normally, right? Yeah, almost always. And a lot of these programs will keep track of what restaurants you visit or what malls you go to. Then they'll come back to you and say, can you write a review on, we see that you went to Texas Chicken at M3, which is a mall near here, right? Can you write us a review? Now keep in mind that particular database is keeping track of the fact that you went to Texas Chicken in the M3 mall. Later on, they can sell that to M3 to say, these are the people that have been to your mall lately. Right there. And now M3 can now target you for a flyer, a mailing, right there. So these people keep track, that's there. You don't think Facebook has got that GPS turned on for no reason. Facebook is one of the biggest sellers of big data, along with Google. Google Maps is not just helping you find your way from point A to point B, it's also keeping track of the fact that you went to point B, right there. So all this information is being bought, packaged up, and sold, and that's big data right there. Right there. So big data deals with applications that deal with massive amounts of data right there. Now, again, you got to ask yourself, why is somebody spending so much money to collect all this data unless they have a use for it? Right there. Google is not in the business of designing free software for no reason. Right there. Google Maps, or what's the other one, Waze, that people use. Waze is free, right? How does Waze make money if it's free? They don't charge for its software. they have to make money somewhere, right? Well, so they're selling something. And what they're selling is you, the user. You use ways to go from point A to point B. All right. Here we've got a user that's a known user. You set up an account with them. You give them an email. They can use that email to reference you back to other big data databases. They know that your name is Muhammad Arif whatever, right there. They find through the system that you're 24 years old and you're a student at UniKL. You're originally from Perak. Right now you're living in Gombak, student housing, and you like to go to M3 Mall. You like to hang out at Wanza Walk. You tend to eat a lot at McDonald's and Texas Chicken and KFC. That there. You also eat at a lot of Thai food stalls right there. So they also can see what groceries, where you buy your clothes, because you stop at various clothing stores from time to time. Then you log on to Lazada and you buy this from Lazada. That there. They can deduce whether or not you're married or single based on the things you purchase and where you go, your schedule. Before long, they know more about you than you know about you. And I'm not trying to scare people about big data, but this is the reality. This is what big data is about, is gathering information and selling. And why do they want to know that? They want into your wallet, right? Now, they're not into your wallet in the fact that they're going to hack into your bank account and steal your money. But they want to know what emails to send you in order to get you to buy something. For example, I buy a few things from Lazada. And those who are not familiar with Lazada, it's an online shopping center there. In the States, I buy from Amazon. Of course, talk about big data collectors, Amazon is one of the top dogs in the U.S. They collect data on everything right there. And I buy something from Amazon or Lazada, my inbox is inundated for the next week or two for related topics. I buy a computer motherboard, from Amazon or Newegg or some vendor that's there. And once I buy that, then I get emails for processors, I get emails for hard drives, I get emails for memory chips, because they know that I'm the type of person who puts together computer systems from scratch, because I bought one motherboard. Now all of a sudden they want to sell me anything related to computer components right there. I've now been flagged as a potential customer for those products right there. And for anybody who wants to really get on the bad emailing list, just log on to a porn site, for example, that there. I'm not advocating, don't do it. That there. Trust me, your inboxes will be inundated with really nasty stuff. I don't know that, but 90% of the people that I've had to fix computer viruses, that's how they got them. That there. So don't log on to them. That's an easy way to get computer viruses. That there. So, but again, once you get into those databases, it's hard to get out of them. Right there. So, but those are the three types of. So we mentioned our basic data types, our strings. That there, we'll talk a lot about that. A file is just a very simple, right there. A particular file is an employee file. Databases are multiple files tied together, and then big data is, of course, as much data as we can gather. Right there. This is byte measurements. I think that's where I ended last time. Right there. I'm going to continue on here a little bit. Kilobyte, megabyte, gigabyte, terabyte, petabyte. We typically right now today stop right there. Terabytes is usually the largest data size we're talking about right there. So when we look at a terabyte hard drive, the largest terabyte or largest hard drive out there is about a 10 terabyte hard drive right there. If you look at memory for computer systems, we're typically talking gigabytes right there. The average Cell phone today, if you look at a flagship phone, you understand what I mean by flagship? That's the top of the line phone. So for example, Samsung sells, like, for example, the S7. That's their flagship phone. That's their top phone right there. Then they also sell a lot of minor phones like the A9, the A7, the A5. Those are below the flagship phone. But the average flagship phone comes with about 4 gig of RAM today, right there. So megabytes, again, of course, is, that's there. But when we talk about a kilobyte, that's 1,000 bytes. We normally don't talk about kilobytes much anymore, except for in the embedded world. In the embedded world, we still talk about kilobytes, right? Megabytes, right there, are commonly used when we talk about a number of things. Gigabyte, which is 1,000 megabytes, right there. And notice that this is 1024, not exactly 1,000, right there. When we talk about 1 gigahertz, we're talking right there 10 to the 9th cycles per second right there. So when we talk about frequency, ohms, farads, those types of things, it's 1,000 right there. That's standard engineering notation. In the digital world, it's 1024 right there, which is 10 to the 3rd right there. So that's there. So these are the byte measurements right there. We're not going to get that there. Let me just kind of break away from here. That there. I've talked not quite an hour, but let me just kind of go through a demo of a C program right there, and just kind of show you. I was going to have you do it, but I think we'll wait till Friday, and that's it. We meet 8 o'clock Friday, right? Same time, right? 8 a.m. Okay. And Friday, unfortunately, we have to meet at 8 o'clock because I've got a 10 o'clock class right there. So let me just kind of, that's there. The software that we use is called Dev C++, right there. And I'm going to create a new source file right there. And we have a couple of things we have to do first. Include and as soon as I can find it here, right there, and I'm just going to write a very simple program here. Int main, right there. Every program has to maintain a function called main. Main is the starting point of your program, right there. And int I, j, right there. And I'm just going to have a print f, enter I, right there, scan F, %I, if I can find my %I, print F, enter J, scan. Now I've got a couple of things I need to go back and do real quick. Oh no, I already did that there. Print F, %I times %I equals percent I j I times j. Right there. Now, this is a simple program. Hopefully I wrote it correctly right there. It's very Greek looking, right? It doesn't look like anything that makes any sense at all. Hopefully that there. I and j are variables. They're stored at there. Printf is a command in C to tell it to print. Scanf tells it to read from the keyboard. It's going to read an integer, and I know it's an integer because that percent I is the code for an integer right there, and it's going to place it into I. I'm going to print out again, enter J, scan, then I'm going to scan that right there, and then I'm going to print this out. So this is just going to ask the user to enter I, J, and then print out I times J is equal to what right there. So this is standard. This is a library call right there. So let's just do a file save as. And program 1. Program 1.c right there. So we've done that there. Now project, save, and council application. Program 1 right there. Program 1, save right there. Oh, it added the, actually, we're going to close this particular one right here. Add to project right there. Okay, and let's close this one. All right, so this is our project, so let's go ahead and compile it. And scanf. Notice I got an error message because I forgot, I misspelled the word scanf. I left the F out there, so let's save it. And project execute, compile it. So it compiled properly right there. If I did everything right, it will compile right there. And then execute, I can then compile, run it. Enter I, 8, and it stopped working. What happened there? It stopped working. What didn't it like right there? Oh, I gotta send it the addresses up there. Okay, up there again. That's just part of the fact that I haven't used C in a while, right there. Whenever we pass it, and this gets into more detail than I care to get into, whenever we pass it something we want to change, we have to send its address to it, right there. So I 8, 9, and 8 times 9 is 72. So it worked exactly as I said it was supposed to do right there. So, right there. So this is a simple program. As you can see, it doesn't look very simple. Right there. Our goal over the next week or two is to where this makes sense to you. what we're doing right here. Right there. Again, the key thing here is we define I and j as two variables that we're going to use. Those are both integers. We do a print. Our command for print is printf, right there. We read the keyboard, right there. Scanf reads the keyboard, and we're going to read an integer. That's what the %I means. If we're going to read a floating point number, we would use %f. And we have to tell it that we want to put it in I, but we can't send an I, we have to send it the address of I because we want to change it. And we'll get into more detail on that there. We do the same thing with j, and then we print I times j is equal to I times j, right there. So again, we can just execute, compile, and run right there. 89, 100. And right here, we've got 8,900. So this program works that there. In this particular program, executed in 6.5 seconds, but again, that's waiting for me to enter the data right there. If I just put the data in there, without waiting for that, it runs much faster. But this is our first simple program right there. And we'll come back on Friday and I'll let you do this one here and start with that there. So I'll probably, and I'll explain this in more detail. I'll finish the slides and then we'll go through that there. But I just wanted to end today with a little bit of a demonstration of what a C program looks like right there. That there. So again, this is not a difficult program once but you look at this first. None of you probably have ever seen scanf before, right? But once you used it, it's fairly straightforward. And as you can guess, I made a couple of mistakes in typing this right off the top, right there. And that's because I've been working with VHDL and I've been working with some other languages here lately. And I'm actually teaching the microcontroller course, and we're using Python, which is a different syntax. So me and syntax don't get along too well. And I should also point out that becoming a programmer, you master a syntax for a particular language, but languages come and go in the computer world. They just come and go. My first computer programming language was Fortran. After that, it was BASIC. After that, it was Pascal. After that, it was PLC. Or not PLC, PLM. PLM was the next language I used. After that, it was Ada. Then finally C. So I've been through about 7 languages over the last 30 years right there. And I don't necessarily master every language, but you master the flow of thought of how you would write a program, and then you let the compiler caught up the fact that I forgot to put the F in there. The compiler crashed on the, at runtime it crashed on the scanf, and I realized there was a problem with the scanf, and then it jogged my memory that I forgot to put the ampersand in there, because I have to pass the address. So, and we'll get into why that ampersand is there as the course moves along. Right there, you just watch me write a program off the top of my head, and I don't expect you to realize exactly what everything does, but now that you see it, it makes sense what happens, right? So, all right. That said, I will see everybody bright and early at 8 o'clock on Friday, huh? Oh, that's too early in the morning, but unfortunately, Fridays are bad days because if I have all 3 classes, it's 8 to 9:30, then again 10:15 till about getting close to noon, and then right after that you eat some quick lunch, go for Friday prayers. 2 o'clock or 3 o'clock is my next, because Friday prayers start at 1:30, run to about 2 o'clock, 2:15, get back to campus, get ready for the 3 o'clock class. So Fridays are long days. But today's a short day. You're my only class today, so. All right.